Right. Thanks everyone for joining today. This session today is more like an old-fashioned report out of a work stream from the early days of Loop, if you like. So this has been a very active work stream in recent weeks, led by James. The Forensic Audit work stream has been trying to work out how to support adopters when they meet forensic audit requirements from regulatory or supervisory authorities. So the focus of James's work in particular has been on how to support the forensic auditing process. There is a separate mini work stream within the work stream working out precisely what to log for forensic auditing. But I'm hoping that James might say something about that as well. So if I might simply hand over to you, James.
Yeah, thank you, Paul. Let me just share my screen. I have a bit of slideware to share with you, unfortunately. I hope I'm sharing the right thing.
We all love a PowerPoint.
Yay. Death by PowerPoint. Right,
Got it.
got it. Okay, so today I'm going to give you a bit of a show and tell on what's been happening around forensic audit. Um, this is something that's been around, the concept of which anyway, and some early implementation and code since the very beginning of Loop. Although it kind of fell by the wayside as priorities shifted and requirements kind of eased, and when Loop was in the early development phases, it was less of a priority than some of the other product features. But in recent times, with the really busy adoption processes going on in lots of countries around the world at the moment, the priority for this work has risen considerably. So we've given it some focus and attention. We've certainly focused some resource on it over the last couple of months, and there have been ongoing discussions about the product requirements for this feature for quite a while in the design authority and in the various product groups around. So the work stream created a requirements document, a business requirements document, probably just about a year ago now, I would say. But we really struggled to find some resource to focus on it. But over the last couple of months, I have had some cycles to spend, and as part of some experimentation that's been going on with our use of AI, we've made quite a lot of progress in the last few weeks. So it seemed a good time to present that out to the community to get some early feedback, show you what we've been up to, kind of check that we're on the right track and that nobody sees any issues with anything we're up to. Obviously, this is an important piece of the puzzle for people operating financial services, being able to keep a good record of what's happened in the system and be able to prove that those records haven't been altered to conceal nefarious activities. So let's talk about some of the requirements that we gathered. Forensic audit really, its raison d'etre, its reason for existing is to support the activities of investigators, looking into things that have happened, chains of events, to understand what's happened and figure out who did what when. This is quite distinct from what we would call operational observability. So forensic audit isn't interested in monitoring the performance of the system or providing debug information in particular. So it's entirely separate from a debug log or what developers would call logging, where the application writes out records to a file system somewhere to record all the intricate details of the steps that have happened while processing the various algorithms involved in moving the money around in the system. This is about creating distinct records of significant events that happen and making sure those records can't be messed around with. The key use cases that we're targeting here are regulatory audits, so tracking payment events, and in Majorleap world, that's the prepare, the fulfill, or reject of a payment. We need to be able to provide evidence in dispute resolution, potentially between DFSPs. So having some unalterable record of which financial transactions were processed by the system and how the money's moved between various parties is important. Some regulatory domains require audit capability for just basic table stakes compliance. A really important cybersecurity aspect of any financial service operation is insider threat. Unfortunately, the world has become increasingly aware over the last few decades that probably the most dangerous people when it comes to potential for stealing money comes from people who have high-level access to financial systems. So a forensic audit is a way of detecting any malicious activity by an employee or an insider within your organization. We spent an awful lot of time discussing what events should be part of this forensic audit and what should not be part of the forensic audit. As a rule of thumb, one Forex transaction passing through a Majorleap hub can involve as many as 24 different API requests. So one transfer of money from one end user to another can cause 24 separate API calls, and a factor of 5 or 10 magnification factor on that, if you take into account all the inter-service calls that happen in the microservice architecture and the different parts of the system talking to each other to orchestrate the operation. That results in a very large number of events happening within the system along the path to move money from one account to another. So that gives us quite a gnarly problem to deal with. If we're talking about a switch that can handle several thousand transactions per second, you add a factor of 2 times 10 to that, you could be looking at 20,000 events per second that potentially are auditable. That's a very high performance requirement. So in order to make sure we're not wasting resource recording events that aren't really significant or important enough to be part of that forensic audit, we gave a lot of thought to filtering that set down to just the most important things, the things that would be really, really important to support an investigation. So things like operator events, so your insiders, your people, your employees running the switch when they log in, log out, anything they do around managing the accounts in the switch, creating accounts, changing the status. As I already said, the important stages, the phases of the transaction lifecycle, the prepare, the fulfill, the reject and timeout, etc. Any changes to permissions and roles within the system, settlement operations, all of those events were deemed to be worthy of including in the financial audit. And I see a comment from Warren in the chat. We should only be concerned with boundary events. Let's open that discussion again, perhaps. We've had a number of sessions in the DA to discuss that as well. But certainly all incoming API requests, but the switch boundary, as Warren mentions, they're important to include in the audit trail as well. So what do we capture in each audit entry? Well, we capture a timestamp, and the timestamp from the view of the source service. So for say an API request from a DFSP reaching the switch, that would be the timestamp from the view of the API adapter in the modular loop switch. Error process ID of the actor, so which actor in the system has initiated this request. So that might be the ID of the DFSP sending the API request, or it might be the user ID of the logged in user for an administrative action. And some description of the event, including which resources were affected, with the type and ID to enable filtering. The source IP address, the device ID, the application name, the version. This just gives further drill down to figure out where the requests are coming from. None of these are perfect in and of themselves. I mean, source IP addresses can be faked. We know that. And whether the action was successful or fail or not. So that can be important if you're trying to figure out if somebody was tampering with the system, trying to make something happen, and they didn't succeed. You might see a series of failed attempts to change a limit on an account, for example. That might give you an indication that somebody's up to no good. And state changes. So what was changed? What was the state of the resource before the action, and what was the state after the action? Again, all to support after the event forensic investigation. Also, any API request headers and bodies as well. So that is intended to give you a full view of the context, what was going on at the time, the resources that were affected, the changes in the data, and who did what. So we have some kind of requirements about the integrity of the audit log, the performance and the queryability of it. So our functional requirement number 3, immutability. This is one of the really critical aspects of the audit log. It absolutely must be detectable if somebody changes an entry in the audit log. That's a really core principle of what we're trying to achieve here. So those of you who are of an engineering disposition will know that anybody who has root access to any operating system can make arbitrary changes to a file system. So your infrastructure engineers can edit files on your file system. It's very, very hard to stop that. Even with the best tools and practices and processes around, it's very hard to prevent that. So we take a slightly different approach and we say, well, okay, there is a risk, however small, that an audit entry might be changed, but there are things we can do to make sure that we can tell if something's changed. And I'll get on to a bit more detail about that in a second. But obviously, the audit log needs to work in real time, so it needs to be able to capture these events and record them in this indelible way as fast as the system is processing. You don't want to have your audit trail falling behind the events that are happening in the system. You need really strong integrity mechanisms, and those need to be mathematically proven, so they would stand up to scrutiny in a court of law. Cryptographic hashing and digital signatures are such mechanisms that we use. You need to be able to ask questions of the audit log as well. You need to provide an interface so an auditor or an interested user can drill down and find the events of interest to them in their investigation without too much trouble. And as I've said before, every single entry needs to be mathematically provable as to whether it's been tampered with or not. And luckily for us, there are mechanisms to make that possible. I've alluded to scalability before as a non-functional requirement. As I said, we have this explosion of events. One single financial transfer can result in a large, 24, 25, maybe even more for some operations, number of sub-events that happen within the system to make that particular business process happen. So we've gone for a system that's horizontally scalable. So ingest rate, the rate at which we can accept audit events and write them into this indelible log needs to be able to scale. And it needs to be cost effective as well. So storing a very large number of events on a disk in this cryptographically secure way can be quite expensive. So we need to do our best to make sure it's super efficient and we don't waste any CPU time or disk operations or network bandwidth while we're doing this. The storage itself needs to be cheap. So an operator who's recording, many millions of audit events, tens of millions of events per week, doesn't need to spend many thousands of dollars on storage infrastructure. Storing this large number of events long term into the future can be expensive. So you need to be able to configure a retention period. These are typically defined by regulators. Regulators in your domain will say how long you need to keep your financial records or your audit records for, and that's typically a number of years, 5 years, 10 years. But we need to ensure that the audit trail is configurable such that we don't waste storage long term. Time stamps and time synchronization is important in this system because the exact moment in time when an event happens is an important consideration when trying to piece together a chain of events that led to a particular outcome. It's important that you can have some certainty about the time of those various events, the relative time, not just absolute time, that those events happened. So we've introduced some mechanisms to try to defend against time-based attacks. I'll talk a bit more about that in a second. But one really other important thing, and something that's come up in the community before, is a fail-safe behavior on the audit trail itself. The product folks in Moduloop have made it very, very clear that this requirement is very, very strong, perhaps the strongest of all the requirements, that if an audit trail entry for an important event of concern cannot be made, the operation shouldn't be allowed to complete. So we shouldn't allow any significant event to happen if we can't write it securely to the audit trail. That has some implications on the system design. So security and compliance requirements, well, best practice.
James, if I can interrupt, do you want to take questions now? Because Warren has his hand up, or do you want to leave it till the end?
Sorry, I wasn't paying attention to the hands up in the room. Yeah, we can take questions as we go.
Okay.
Sure.
Well, go on, Warren.
Okay. Yeah, that requirement, bearing in mind that it doesn't exist at the moment as a function of things, has just put auditing in the line of business for everything else that happens, right?
Yeah.
Yeah.
True.
Have I understood that right?
You have, Warren, yes. Absolutely.
Okay. All right.
Now,
and that requirement has been made because somebody thought it was a good idea, or because there's industry standard best practice, some documentation outside of our little ecosystem that says that that's what we should do.
I will defer to my product colleagues to answer that question.
Yeah, I'm not entirely sure what the point is of an audit log if you can somehow disable the logging and carry on with potentially fraudulent transactions. It does seem a bit of a loophole, Warren.
Yeah, no, I agree. It's worth discussing.
Yeah.
The other thing about, of course, the way Moduloop works is it creates a coherent set of certainly in the transaction layer. It ensures that everything is signed off and is therefore reconstructible from the original messages, right? So, in effect, creating a audit history at each participant within any transfer, right? So,
Yeah, so one important thing, Warren, the ledgers, so financial events, we are trusting the ledgers. So we had a lot of discussion in the DA and in the work stream about whether we were actually trying to duplicate what the ledgers do,
Yeah.
recording financially significant events. And we did deem that no, the ledgers are trustworthy. We have to trust the ledgers. If they're not trustworthy, we might as well all go home. The ledgers have been designed to keep accurate financial records of movements between accounts. So we're not recording the details of the inter-account movements in the audit trail.
Yeah, that one was the subject of a great deal of odd, shall we say.
But I do think it's worth saying that the set of events that we think are auditable at this point in time is just what we've arrived at through a very long and arduous debate. And there are still people on two sides of the camp as to what's auditable and what's not auditable. So if anyone here has any strong opinions, I would really encourage you to come along to the Forensic Audit workstream call, which happens every other week on a Thursday at 9 a.m. UTC. If you wish to be invited to that, please just reach out to me. Email us Slack. I see another hand up. Yui.
Hi, Jane. So I'm a new contributor, so and try to learn about the project around here. One question I have, and maybe I miss it somewhere else, is in terms of what required to log, is this something that we can work with regulators themselves? What's like what would be required to do in order to facilitate like the type of event that we log for audit?
Yes, that's a very good question. So the design of this forensic audit subsystem is such that the source service, the service that's recording the events, sending them to the audit service, can decide which events to send. So although we've made quite a long way implementing the audit service itself, we haven't done the integration with the other services like Central Ledger and the ML API adapter, the ALS and the service. We haven't done that integration yet. So the jury's still out on that. In fact, there's it's open as to whether there could be some config for that. It's being discussed. Paul, you have your hand up.
Yes, just to say, you raise a very good point, and at the last workstream meeting, well, we've had a number of workstream meetings where members of the workstream have disagreed very politely on what should be audited and what shouldn't. And so a sub-working group has been established to essentially put together a straw man of what should and shouldn't be audited. We've had multiple attempts at that, but now we're kind of formalizing that. And so Michael Richards and myself are doing that because we are on we're not necessarily totally aligned on this. And we've also agreed, Michael and myself agreed that we should take our straw man and we should try and present it to as many regulators as possible just to get their feedback on it. And Michael has undertaken to use a number of channels he has available to him to try and achieve something like that, to try and engage a regulator long enough for them to actually give an opinion.
Got it. Awesome. Thank you so much.
And Michael, I'll just hand over to you.
Yeah, so I was just going to add to that. Our experience is that regulators are not very happy at being asked to pronounce on general questions.
Yeah.
So they're not very happy with if you go to them and say, what should an audit log, a forensic audit log contain? That's a question they don't like. The question they like is if you turn up and say, this is what our forensic audit log contains. Are you happy with this?
Got
They
it.
find that a much easier question to answer. So that is that's the route that, as Paul says, we are following at the moment.
Got it. That makes sense. Maybe one quick follow-up on that
Of
is,
course.
is this something that, like, say we can engage with the regulators, say in say, I know some of us are from UK and US, that within the UK or US regulator, just the ease of engaging sometimes can happen within in the same country. Would their feedback also helpful, or it's better to engage with the country where the system are deployed directly for feedback in this case?
I mean, my personal opinion is that regulators in advanced economies, literate economies like the UK, US, Singapore, places like that, don't necessarily have a very clear idea of what payment systems in emerging economies are really like. And therefore, my personal opinion is that it's better for us to talk to regulators in our target jurisdictions rather than talk to the regulators in, as it were, our home jurisdictions. But that's just my personal opinion.
That's a fair one. Thank you. Thanks so much.
Okay, thanks. Yeah, I just will say that the design and the implementation that we've come up with so far has deliberately not made that set of events hard coded. So it's very open at the moment. We can change our mind about that as we go. And also, we've paid a lot of attention to the performance of that right path. So if audit is disabled for any particular reason, if you don't need a particular set of events, the slowdown, the impact on the performance of the system is as minimal as possible. There's a circuit breaker pattern been used to avoid any unnecessary code path being processed. Where did I get to? Okay, so strong encryption between the source of the audit log, so the microservices sending the audits, audit trail events, and the service receiving them. We've got strong encryption between those two endpoints using TLS 1.2. With mutual TLS enforced between those two. So this actually doesn't rely on the service mesh. This is point-to-point encryption in the service layer using a special CA purely for the audit trail with PKI certificates being issued by the internal HashiCorp Vault CA itself. So it's completely isolated as a security domain. We can use AES 256 encryption at rest on all the stored audit data. So there's two file systems where audit events get written to. One is an S3 based file system, which can reside on top of any other normal file system that supports AES 256 encryption. All of the signing keys, all of the private key material is held exclusively in HashiCorp Vault. I'll talk about some of the technology choices that we made towards the end of my talk. Role-based access control across all the audit infrastructure, using the same ORI stack that everything else uses in the existing modular world, so JWT validation. Strong separation of responsibility between the different components of the audit trail services, so they only have permissions scoped to their particular operations. So the service receiving the audit events never has access to any of the private key material for any of the source services and vice versa. And all of this has been designed with the following compliance targets in mind. So ISO 27001 PCI DSS, for example. So all of the choices we've made are in line with the recommendations of those. So next I'll talk a little bit about the architecture and the system design to try to meet these requirements we've set out. So there's 4 packages, 4 separate code chunks that make up the implementation. There's a shared library, which has a bunch of type definitions. All the code is TypeScript, following the modular recommendation that the new code should be built in TypeScript. This also has a signature service in it, which is a general implementation of the, well, it's not an implementation of the ED 25519 algorithm. It's just a wrapper around the Node.js implementation in the Node.js core crypto library. There's some utility functions in there as well for manipulating the key formats that come to and from Vault. There's a client library. Now this is the chunk of code that gets embedded into a service that generates audit events. So Central Ledger, for example, in the next step of this project, will have a new dependency on the audit client library. And this just exposes a very simple interface to the service to generate an audit payload. It handles all the signing and the mutual TLS connection to the audit ingest service, and it handles all the HTTP messaging, manages all the certificate and key life cycle. So the audit call is blocking. I'll talk a bit more about that in a second. I know there's various different opinions on this around the room. Then there's the ingest service itself. So this is the thing, Node.js implementation that receives audit logs from the source services. This is horizontally scalable. It performs a number of jobs. It makes sure that the incoming audit events have been signed by a known private key. It countersigns the payload. It writes the body of the payload to S3 storage, and it writes an index to a piece of technology called ImmuDB. So before it writes that S3 body, it takes a hash of the body, and it writes that hash into the index in ImmuDB. There's 2 listening ports on this service, one for the Kubernetes deployment that just reports on the health, and then there's the TLS protected endpoint on the separate listener. There's also a query service. The query service is for users to ask questions of the audit trail. Again, this is using Fastify, which is this kind of newer generation of super fast Node.js HTTP framework. This sits behind the Ori RBAC stack that we use everywhere else. It has two main endpoints. One is to search through the index of audit entries. And there's a number of fields you can search on and filter on. The type of event, the actor, the resource, the transfer ID, for example. And then you can request the details of those events that you find in that list. When you request the detail, the service re-verifies all the signatures, checks the hashes, and it also verifies the Merkle proof. There's 2 Merkle proofs that ImmuDB provides. Apologies to non-computer science students. A Merkle tree is the basis of the tamper evidence mechanism that we're using. If you don't know what a Merkle tree is, it's worth having a little look up on Wikipedia. I always I'm highly hesitant to give Wikipedia as a reference, but in this case, it gives a pretty decent explanation, a simple explanation of what a Merkle tree is. But it checks all the cryptographic proof about the record to make sure it hasn't been tampered with in either the index or the S3 body. Before it returns a result to you, it will tell you whether that entry has been tampered with or not. So the right path, keeping my eye open for any raised hands at this point. So the right path, the source service makes a call on the audit client. Remember that client library, and it passes in an audit entry. The client library canonicalizes the JSON. I know Michael will be pleased to hear that. The JSON payload is canonicalized and it's signed with the source service's elliptic curve key, and it gets sent off over MTLS to the ingest service, which checks the source signature against the public key, and if everything is good, it countersigns the entry and makes two further writes. One is to write the full JSON body to S3 after it's taken a hash of it, and records the SHA-256. And then it writes a lightweight index record to our Merkle tree database, including the entry ID, the S3 hash, all the timestamps and the fields that are indexed for searching. And then it returns back to the caller, the source service, the index transaction ID and the S3 entry ID. So that can be written out, for example, to the debug log. So if you're debugging a service, you can see audit events and correlate them back to the normal debug log. In the read path, as I said, the auditor can query the indexes to get a list of entries, and then they can drill into each entry in detail. So that's behind the RBAC wall that Oathkeeper and the Oristat gives us. It makes sure that the caller has one of the roles permitted to query the audit trail. If it does, it looks at the index record first in the Merkle tree database, and it uses this method called verifiable get, which returns actually all the source material you need to do your own cryptographic calculation to prove that the record, well, two things about the record. One, that it's included in the current Merkle root, so that is a genuine record from the audit trail, and something else called a linear proof, which proves the position in the audit trail of that entry, so where that audit exists in the list of audit entries. That proof is verified completely independently of the Merkle tree database by the audit query service itself. There's a small detail that when you verify the state of something, you want to verify the position of something in a Merkle chain, a Merkle tree, you need to anchor it from a known good position in the tree. Now, when the tree is small, it's easy to verify all of the proofs. It's quite computationally easy to verify all the proofs up to the particular point at which your entry exists. But when your audit trail is very, very large, you might have tens of millions of records in it, that becomes quite time consuming to recalculate the entire Merkle tree. So what you do is you take hops as you query from the start, you build a new trust anchor, and that anchor moves forward through the audit trail. And the query service stores that trust anchor, again in Vault, in a very secure way. So it doesn't have to recalculate the entire Merkle tree with the Merkle from the root every time you fetch a record. So that's for performance and efficiency there. So once that index entry has been verified, the query service checks the content of the body from S3. So it pulls the body out, recomputes the SHA-256 hash, and checks it against the hash that we stored in the index. If those hashes don't match, then you get a flag set in the response, so you know that the body or the index has been tampered with. There's 5 different flags in the response from one of these gets to tell you which part of the verification might have failed. So you can tell which part of the audit record has been manipulated. And then finally, it re-verifies all the signatures across everything. And it will set 2 flags on the response to tell you whether the signatures are okay. So I think in talking, I've actually covered most of the details of the way we cryptographically provide that tamper evidence, but here's a kind of summary. There's 3 layers. The double signature being layer 1, so the source service and the ingest service both signing the audit entry. That means that neither a source service or an ingest instance or a compromised one can forge a complete entry. The second layer is that content addressed S3 with the hash over the body that's recomputed on every single read. So any single byte change in the S3 body immediately changes the hash, which surfaces as a flag in the read record, so you can tell that the body's been messed with. But that hash, the fact that we store that hash in the Merkle chain means you can't change the index record. So you can't change what the system thinks the hash is as well, without breaking the entire Merkle tree at a certain point, which tells you the precise point in the tree in the audit trail where somebody has changed one of the records. Then there's the Merkle proof chain itself. This is an append-only ledger, where, okay, simplistically, the Merkle chain is just a series of hashes, but by including the hash of the previous transaction in the next hash, you form a chain of proof that proves that no one record in the chain can be altered, because you break all the hashes in the next records and every record subsequent to that. So yes, it's very hard to forge fake the Merkle tree, to alter the Merkle tree. It's computationally quite hard, until, of course, quantum computing becomes commercially available, or some clever mathematician solves P versus NP. If either of those two things happen, then we're going to need something other than a Merkle tree for our audit trail. Hopefully those are some years away. Right, we did a bunch of... Michael, hello.
Sorry, I just wanted to add to your last comment that if either of those things happen, everybody is in serious trouble.
Indeed. Yeah, it won't just be us.
It won't
Can
just be
I
us,
push
and it won't
back
just be
against that
us.
a little?
Sorry, Paul?
Can I push back against that a little?
Yeah, please do.
Just to point out that we have not actually yet created any audit logs. So we don't have historical vulnerability to post-quantum crypto, or sorry, crypto computing attacks. And
It would be a solution not to create any audit logs.
a solution would be to create our audit logs using cryptographic algorithms that are resistant to quantum computer attacks.
Yeah, it'll be the hash, the hash computations.
Exactly what I'm looking at, James.
Yeah, indeed, yeah.
Given that we are at some point going to have to go through the entire code base looking for places that might be vulnerable to quantum computer attacks, maybe we shouldn't create more code base that will need changing at some point. Because if ever there was something that is going to be subject to harvest now, decrypt later attacks, it's the audit logs.
Yeah. Well, yeah, indeed. Yeah.
Just a thought. Sorry.
Yeah. I mean, it's something that's been on our radar in other areas of Mojolib as well, the whole quantum thing, P versus NP. Yeah. It's so already we have PRs to change our default cipher algorithms for all our inter-service communication to post-quantum. That's to protect the outside boundary, but internally, inside the system, we'll need to do something about that.
Yeah,
Right.
I'm just making the somewhat trivial point that maybe we shouldn't be creating more code that needs to be changed.
Well, yeah, I don't think we have. I don't think the world has settled on what they think the right thing to move to is in terms of hash algorithms as yet.
No, but hash algorithms, as you well know, are built on some of the core cryptographic algorithms.
Definitely, yes.
So which have been fairly well defined.
Yeah.
For the post-quantum world. I just think we need to think about it. That's all. I'm not asking you to come up with a solution right now.
Well, all I will say is that we haven't implemented any of the algorithms ourselves. We're using the Node.js implementations, which are all,
which are built on the open source of implementations of the cryptographic algorithms. I know, because that's good practice. Yeah.
So as soon as those new algorithms become available, it's relatively easy for us to change to them. Okay, so here's the threats we thought about. Rogue actors changing log entries, DB admins, people breaching various services or containers at runtime and fabricating or forging entries, given that they might have their private key material in memory, replay attacks, and so all of these are stolen keys as well. We've thought about how to mitigate each one of these. So I mentioned clock skew. Yeah, so even though it might be possible to steal a key or to do a replay attack, the fact that as long as the ingest service has a good clock, it can tell whether somebody's sending an entry that's outside a certain time window that was supposed to have happened too far in the past or might be too far in the future. So the ingest service can block that. The timestamps recorded on the entries there give us some mitigation. There are still some known security gaps with this, and I'm going to say, and any other audit implementation that we've ever seen or that's been represented in the literature. So if somebody does compromise a live service, all bets are off. There's potential to interrupt the network at certain selective points or inject packets into the network to selectively omit entries from the audit log. Is very, very difficult to do. And there are mitigations like reconciliation against the central ledger transaction log, for example. Tampering with Vault itself. Yeah, the most vulnerable part is the infrastructure. If somebody can breach your infrastructure and gain root access to your containers, your container runtimes, then you're in big trouble anyway. So key management, all our private keys managed by Vault. They're these ED25519 keys. As a crypto algorithm, this is fast. It's regarded as very, very secure, but it's also very fast and it has quite small keys. So it seemed like a good choice for something that was on the hot path. We never store any of those keys in config or on disk or in environment variables. Each service is locked down so it can only read its own keys. We have zero downtime key rotation implemented as well. So at any point in time, either your Vault agent service or an admin can rotate the keys. They have default time to live and they rotate their keys automatically anyway, but at any point in time you can rotate the whole set of keys with no downtime. So the mutual TLS certificates locked down to just the Vault CA, again a separate security domain. So if you can obtain a TLS certificate that's been signed by Global Sign or one of the other big CAs on the internet, that's not going to get you anywhere because we've locked it down to just the Vault CA. And we've done the Vault access control. We're using following best practice using app role type scoping, which makes sure that we limit the read access to the private key material. Okay, synchronous blocking ingest with no queue. So this was really important to give us that core guarantee that the source service wouldn't allow an operation to continue until we knew the audit record had been actually written to the final storage with all the cryptographic guarantees. So there's no window between when the action occurs and when the audit record is persisted. Again, we had lots and lots of discussions about this. And some people suggested queues. Well, why can't you just write the event to a queue, worry about ingesting it into your secure storage after the event, allows the service to carry on well. The source service can only ever really know that the message has reached the queue, not whether it's actually been written to the secure storage. The queue will still fill up if you're in an overload situation and you're ingesting messages faster than you can write them to your secure storage. It doesn't help you. Queue doesn't help you. It just gives you a bit of load leveling rather than increased throughput. There's also a couple of I see your hand just a sec.
5 minutes, James.
Oh goodness. Okay, I'm nearly at the end. A couple of nasty edge cases that that exist if you use a queue between the source service and the secure storage. So this point in the design, we ruled it out. So the correct response, rather than adding a queue to the system to throughput pressure, is to scale out the ingest service horizontally. However, this is a trade-off that we're aware of. We've made the decision in full knowledge of this, that there's potential to add latency on every audit write. And there's a super hard dependency now on the ingest availability. And Warren, I think your point earlier on called this out. However, we have mitigated this as best we possibly can right now by using long-lived TLS connections, which means there's no TLS handshake overhead. But also we've tried to keep the code paths in the right path to an absolute minimum. Right, the double signature method and split storage. Well, again, the double signature scheme gives us some cryptographic guarantees, and the split storage means our Merkle tree is super efficient because we're not storing big chunks of data in it, just a few small fields for indexing. While we still do have the ability to have very, much larger and richer information on each audit trail. Tech choices ImmuDB. It is open source, but it has a business source license similar to Redis these days. So we were quite careful to make sure we didn't land ourselves with a nasty licensing issue there. It does everything you'd want. If you were going to implement a Merkle tree storage mechanism, you'd end up with building something like ImmuDB. The options we had were either to build our own on top of something like Postgres or to use a blockchain. And neither of those seemed preferable, given that when it comes to this, anything crypto, it's better to use something that's tried and tested and open source that's been verified by a large community of people rather than try to invent your own. So S3 compatible storage for the audit bodies, we chose that because it's large, scalable, and relatively cheap. HashiCorp Vault, well, I mean, that's almost a table stakes no-brainer for most people these days. Anything you're doing in Kubernetes and you want secure secret storage, HashiCorp Vault is your go-to option. It does actually support HSM storage for the private key material under the hood for people who care about such things in production. As I said, we chose the signature algorithm because it's super efficient, but cryptographically very strong. We chose Fastify rather than some of the older HTTP frameworks that some of the modular code has, like, the name of which has escaped me. And TypeScript, because over time we generally want to refactor the code base as much as possible into TypeScript, just because it eliminates a class of bug, potentially. So limitations, I've talked about some of the limitations already, but even though the log can prove every entry it contains is authentic and that it's not been tampered with, you can't guarantee that you have every event in the log. Right now, the ImmuDB, in the current deployment that we've got implemented, we only have a single node. So there's a small amount of work to add the ability to deploy those in an HA cluster. It's a relatively small amount of work, like I say. ImmuDB natively supports follow-on replication, so we just need to configure the deployment to do that. The Vault audit log itself is an important piece of the audit trail because it's a record of what's happened to your private key material. So we need to add something around operational tooling to export the Vault audit log to make sure it's stored securely externally. And something that's kind of work in progress at the moment is the ability to store binary request bodies as well as JSON request bodies. So the plan is to base 64 encode those and store them in S3 in the same way and hash over them, same way we do with JSON request bodies. So what have we built? We've built a tamper-evident, cryptographically verifiable audit log for Mojali. The synchronous write path with full cryptographic verification on every read, production-ready security posture, and we have addressed all the requirements we set ourselves. So, with 1 minute remaining, does anyone have any further questions? Obviously, if there's not time for questions now, there is a Slack channel. I posted the Slack channel name in the Zoom chat. It's ws-forensic-audit. Please join the Slack channel. Like I said, there's a workstream call every 2 weeks on a Thursday morning UTC time. You'd be very welcome to join if you're interested.
Thank you, James. I'm sorry, there are no time for questions. I would encourage anyone who's interested in this to come to the join the Slack channel and come to the workstream meetings. Believe me, we have all these fun arguments every 2 weeks.
Yeah.
It's a really important workstream, and please come along and contribute. Give us your opinion. Okay, with that, I'd like to thank you again, James, and close this down. So,
thank you very much, everyone.
Thanks very much.
Thank you, sir. Thank you.
See you
Thanks,
again.
James.
Thank you very much.
Thank you.
Bye.
Bye, folks.